We are now recording. Let's get started from current slide. And before we do, let me just go over where we are. We've already hit part of it. Going to start in chapter 18 today, where we left off last time, and that was on page 460. We didn't get very far at all in this. But it's a relatively short chapter. We'll see how we progress. If we are finished by 1:30, which is not very likely, but if we do, take that back. By 1, okay? We finish by 1, which is not very likely, but we might. Then we'll go on to do the lab, okay, on this chapter. If, however, we're not, we'll keep going until we get to a point where we can stop. And no later than 3, I'll give you the test on chapter 17, okay? When you finish the test, you can go home. The lab today is relatively short. I think you'll find it fairly interesting. Actually, a hands-on physical lab, literally a wet lab, they call it, okay? And then the trouble is the lab is very short, as I said, so therefore you're going to have to do some questions to fill up the rest of your 25 points in the lab, and we'll talk about that later. Okay, so that's today. Tuesday, what's happening? You won't be here Tuesday? Or Thursday. Well, Tuesday, you know, it's a field trip to planetarium. Okay? We'll be leaving here right at 12 o'clock. Now, you said you drive yourself, right? Did you need a ride? Oh, you're going to take yourself too? Okay, and Amber's not going to be here. I don't know about James. So Tuesday is a field trip. We'll leave right at 12. If you're somewhere else and want to go straight to Sanford, you certainly can. If none of you are riding with me, then I'm going to just leave at 12 and get over there as soon as I can. Okay? The field trip consists of the show from 1 to 2. So we'll be leaving Sanford to come back here around 2 o'clock. Should get back here by 2:45. Depending on traffic, it could be 3. And then we have class until 3:30. Now, if y'all don't want to come back, that's okay too, because you'll be there for, enough time that we would have had class and lab. The lab is technically 2 to 3:30, so if you're there past 2, then you get counted for the lab too. But I'll come back and finish, because we just can't afford many other misses. We already missed last Tuesday. We missed the Tuesday that I had to be in New Orleans. So sorry, we've already lost 1 week. And there is a fair chance we'll lose another day. And here's the story on that. I think I may have told you before, I've been assigned, yay team, to be on a biology screening and search committee. They assigned me week before last, and they said, meet in the personnel office over on the Birmingham campus, of course, last Monday, not this Monday, but the one before that. They gave us 2 times, once in the morning and once in the afternoon. Well, I couldn't make either one of them because I had class all day long on Monday and Wednesday. So I said, can I go Tuesday after this class? Get out at 3:30, try to be there by 4 o'clock, which I was. When I got over there, they said, oh, you really didn't need to be here. It's all online. Well, there had been emails going back and forth about when I could be there and all that kind of stuff, and I had to be there, and they said I didn't have to be there. So that was 30 minutes wasted driving over there. I could have been working here and getting stuff done. But then once I was there, they couldn't get me logged on because it was all online, and it's a new system to the college, and they couldn't get it to work right. They were having to make phone calls and stuff, so that took another 45 minutes to an hour. So finally, they were able to get me on, and I had time to review 3 applications because all that wasted time. And two of the three, I disagreed with the rest of the committee members. So I thought, what is going on here? They just didn't meet their qualifications, and they said they did. I couldn't see why. So anyway, but no one was there to talk with. So anyway, I took home the rest of them. And of course, Wednesday of last week, I couldn't do anything. I was here teaching all day. Got home at close to 10 o'clock or afterwards, so no doing there. But Thursday, every moment during my office hours that I wasn't registering students or doing other things like that, I was going through the screening, okay? Didn't get to finish on Thursday because of all the other interruptions, so I took them home and over the weekend. And we were out of town, so I didn't have lots of opportunity, but I managed to get all of them done and everything sent back to them. And then I started grading papers. I had gone a whole week without grading anything, so I had a stack so deep, okay? And I got all the papers graded, but I didn't get a chance to put anything in Blackboard. I just ran out of time. So yesterday, I had more than that many papers done. I've already graded some today. I graded 2 classes and part of the third class this morning in the short time I had before lunch. So I hope for the rest of the day finish grading those papers and maybe even get a chance to put things on Blackboard. But I know I've got one student who came right as I was trying to eat lunch wanting to register. And he had met with an instructor yesterday and he wouldn't let her register. He wanted me to talk with her. Or, I don't know. So anyway, he came this morning while I was trying to eat lunch just before this class. I said, I got class starting in 20 minutes. I haven't finished eating. And he said he could come back at 3:30. So I know I won't have a certain period of time to grade papers because I'll be registering him. I've got to leave today at 5:15 because I've got a meeting in Birmingham at 5:30, which I'm not going to make on time, but I'll get there as soon as I can. So I think we got perfect attendance. Way to go. Okay. All right. I was just going over this now. You know, okay, let me go over the rest of what I've already said. I'll try to make it quick. Today we're going to start in chapter 18 where we left off last time. Try to get as much done as we can before 1 o'clock, okay? If we finish the chapter by 1 o'clock, which seems less and less likely now the more I keep running my mouth, we will have the lab on chapter 18. Kind of doubt that's going to happen, but we'll see. If we finish and we still have time to do the lab, we may try to squeeze the lab in. It doesn't take that long, and it's a very short lab. Part of the lab you're going to have to do on your own because it's answering some questions, because like I said, it's a very short lab. There's only 10 points worth of stuff that we'll do in the lab, and the other 15 points will be answering questions from the chapter. Okay, so anyway, we'll see if we can get that in. But the last 30 minutes today, whichever, whether we do a lab or not, the last 30 minutes today is a test on chapter 17. Okay? Now, Tuesday, what's happening? Field trip. Okay? And Amber won't be here. The other two said they're driving, right? Okay. What about you? Do you need a ride? Tuesday, we need to be there between 1 and 2, so, be there before 1 and last till 2. But I will be driving. I can carry 2 or 3 people in my vehicle if you want to ride with me. I'll be coming back here to campus after that's over with, and I'll conduct class whether anyone's here or not. I'll record it so it'll be there for you to hear, but we just can't. Say again? At Sanford University, right. So you'll drive straight there? Okay. And then it's up to you whether you come back here or not. Like I said, I'll come back here and finish up the class till 3:30, okay? Okay. Now, so that's Tuesday. Thursday of next week, if we haven't done it, it just depends on how far we've gotten. If I haven't finished chapter 18, we'll finish it. If we have finished 18, then on Thursday, we'll probably definitely have time for the lab. And if I finish it by Tuesday, you'll have the test on chapter 18 too. Okay, so be ready for that on Thursday. We'll find out whether that's going to happen or not. Listen to the YouTube to find out for sure. And then we'll proceed on to chapter 19. Okay. And as I was saying before, I am on a biology screening and search committee, and it took me most of my holiday weekend to get the screenings finished and to get all the papers graded that had been turned in last week. And then yesterday, I got more than this many turned in yesterday, so I've still got that many to grade, or almost that many, well, a couple of them are graded. And then, I don't have any of those that I graded over the weekend in Blackboard yet, so I've got to get Blackboard caught up, and then I've got to get attendance caught up. I'm going to do as much of that as I can today, but I already know I have a student coming by for registration after this class is over with. So that will take a while, but other than that, I've got to leave at 5:15 today because I've got a meeting in Birmingham at 5:30, which I'm not going to make on time, but I need to get there as soon as I can. So I won't have a lot of time this evening to work on it, but I will try to get things caught up over the weekend, hopefully. And then Tuesday is the last. Now, back to the biology screening and search. We're down to 9 candidates. There ought to be 8, but the chair of the committee insisted that someone who had taught 2 years of 7th and 8th grade science, that qualified her to do college biology. I don't see it, but she did. I don't know what the connection is there, but so we're interviewing more people than we should, but hopefully some of them will say, no, I found another job, or no, I'm not really interested, or I can't make the interview. So I'm hoping they're going to schedule the interview all in one day, but the unfortunate thing is it's going to have to be a Tuesday or a Thursday, or I'm not going to make it, okay? Because, I don't know what I'll do, because it's Monday or Wednesday, it's going to knock out 4 classes, and that's really going to be rough. So if we do miss another day because of interviews, that's why we can't afford to let any time go by. So, any questions? Chapter 17? Yes. About what? Okay. Whenever you finish it. Yeah.
And what is considered finished with that?
What's that?
And what is considered finished with that?
Okay, we did most of it in class, so you should be finished with most of it already. Those 3 questions, one about where is the moon moving relative to the landscape over time, where is the moon moving relative to the stars over time, and how is the phasing of the moon changing over time. Those 3 questions are the only ones you should have left to do, because we did all the rest of them in class. And you can hear them on screencast or YouTube video if you weren't here that day. I think you all were, because y'all haven't missed a day since the very beginning. So, okay. And then, like I said, this lab today is probably going to take you a little bit longer, because there will be some questions to answer on it as well. Okay. Any other questions before we move on? And by the way, I have seen the moon a couple of nights recently, so it is out there in between clouds sometime, but you can usually catch it. So, not always. Some nights have been too rainy. All right, so we were talking about seismic waves. I think we were on this slide when we ended. If there are no questions, let's go on. All right, there are 3 types of seismic waves. Okay, the first of these is called a P wave. Now, this P wave, you can think of the P in at least 2 or 3 different ways. One way is primary, the primary wave. Why do we call it primary? Because it gets there first. Primo, 1, okay? First wave to get there. Other way you can think of it is a pressure wave, okay? And that's why it gets there first, because it's a little bit faster, okay? It's also called a longitudinal wave. Now, what do we mean by that? I think there's a good illustration here. If you had a spring, I don't know if any spring does hand out there that long without sagging. But if you did, and you pushed on the spring and pulled back, you would see that pressure thing go to the end and maybe even bounce back. That's a pressure wave, because the pressure is put this way. Actually, when I'm talking to you, if you put your hand in front of your mouth when you're speaking, you'll feel little pulses of air, right? And what that is pressure wave. The pressure carries through the air, hits your eardrums. Your eardrums are very sensitive. You pick it up and you translate what that means. Okay? Those are pressure waves. In other words, the movement of the particle is horizontal, but the wave propagation is also horizontal. When the particle motion is in the same direction of the wave propagation, that's called a pressure wave. Okay? These are the fastest waves. That's why they get there first. And by the way, they're called longitudinal because they go along a straight line. The motion is in that direction, and the compression's in that direction, the rarefaction's in that direction, and the motion of the wave is in that direction. Okay? Now, these are the fastest waves. They move through surface rocks. They move through interior solids. They move through interior liquids. They move through all material. Okay? Gases as well. So pressure waves, P waves, primary waves, go through solids, liquids, and gases. We're only dealing with solids and liquids here. Now the secondary wave, again, the S waves. Two ways at least you can think of these. Secondary waves, why secondary? They get there second, okay? They're not quite as fast as the primary waves, so they get there second. They're also called shear waves, S for shear. Another name is transverse waves. And I think of this, they show a rope here, but I remember when I was a kid, I used to like to do this, dumb me, when we had a hose laying on the ground, right? Watering something or whatever. I like to pick up the end of the hose and do that to it. And what happened? That wave moves down the hose, sort of like the snake kind of thing. Okay? My motion was up and down, but the wave moved down the hose. So that means it's transverse. Motion up and down vertically, the wave motion is horizontal. Okay? So those are transverse or shear waves. Shear meaning opposite direction of the motion. These are second fastest. They're not a lot slower, but just a little bit slower than the primary waves. However, these will not travel through liquids. They only travel through solids. They don't travel through gases either. In fact, you could say they don't travel through fluids, which is liquids and gases. They only travel through solids. Okay? And then the third waves are the up and down or crest and trough waves. And these are, I usually think of them as surface waves. I don't think of them as up and down waves. I think of them as surface waves. These are much like water waves. They go up and down and back and forth. These are the slowest of the three, and these occur where the P or the S waves reach the surface and then travel down the surface. Okay? They don't really, it's S or P that makes it to the surface, and then the surface waves go on from there. Okay? Now, one of the ramifications of this is tsunamis. When they're underground seismic activity under the water, then you have a surface wave, a tsunami, also called a tidal wave, that could wipe out populations near a beach, near the shore. Okay? On land, I don't know if you've ever seen this. I've seen a few pictures of this before. When they've done some of the nuclear testing and the nuclear explosion happens, then you can see the ripple effect in the soil surface. The sands and the soils, you actually see the waves go out like this. So the surface waves are not just water. They're like water waves, but they could be on land as well. And they move outward, sort of horizontal. Those are the slowest of the three waves. Okay? Any questions on seismic waves? Why are we concerned with them? Well, They help us figure out what the Earth's internal structure is. I think maybe one of you or more has asked about this. How do we know what's inside the Earth if we've never been there, if we can't go and find out? Well, we're going to get there in a minute. So the Earth's internal structure, three main zones. The first of these is the crust. Okay? Now this is a picture of the Earth, and this would be the crust. This thin little sort of brown trapping there, that is the crust. It doesn't look very thick here. It's only a few miles deep in most places. Miles deep, that seems pretty far compared to the Earth's diameter. It's nothing. It's just the surface. That's where we live. That's where everything that we know goes about basically is on the crust. Okay? Now, I can't adjust for or recommend or say why they have this other layer. I think I know what that represents, but we're going to leave that alone for now. This thick area here is called the mantle. The mantle is also solid. Okay? Now the crust is mostly solid, except that we have a lot of ocean covering the planet. Underneath the ocean is solid. That's part of the crust. Okay, so all the oceans and rivers and lakes and everything else sit inside the crust, fit into the crust, but then inside that is the mantle, and that's solid. Okay, so the crust is the outer and very thin shell, only a few miles thick at most. The mantle is the thickest part, much thicker, much thicker than the crust. And then the core is the central part. There's an outer core and an inner core. And again, I can almost hear you asking, how do we know this if we can't get down there? We've never much gotten out of the crust. Maybe some of the deepest drilling that ever has happened may have gotten into the upper part of the mantle. Maybe a little bit into the middle part, but not very much. We seldom make it to the mantle at all. We never make it to the core. Okay?
Deepwater Horizon.
Okay?
Wasn't that well below crust?
Okay, no, the well was in the crust. It was below the water, and it was more than a mile deep, but still you had the crust, which is the seabed of the Gulf of Mexico, that was down there. Even in the Marianas Trench, which is the deepest water on the planet, that below that is still crust. Not very thick, but it is still crust there. And we'll talk about that a little bit later too. But very seldom do we get into the mantle. In a few places, it's almost like the mantle comes up to us, but it really doesn't. That's still part of the crust. Now we'll talk about the outer and inner cores later too. I'll go on and tell you now, the outer core is mostly liquid, mostly molten rock. Okay? The inner core is solid again. Okay? Now here's sort of the reason for that. Okay? Gravity. Okay? Gravity is pulling all things toward the center of the Earth. The crust here is being pulled toward the center. The upper part of the mantle is. The lower part, the mantle, more and more pressure there, and you got things bumping into each other so hard, so fast, and such friction there, that melts the outer core. But the pressure is so great by the time you get to the inner core, it's so pressurized that it forms a solid again. The pressure is so great it can't stay a liquid, it goes back to being a solid. Now we don't know much about the solid, but we do know it's there. And we'll see how we got that later. All right, there's your visual. It's the same figure you see on figure 18.3 on page 461. So let's look at the crust. You were asking about it. The crust covers the entire Earth. Now, most of the Earth is ocean, okay? But under the ocean is the ocean crust. Believe it or not, that's the thinnest of the crust, much thinner than the continental crust. It's mostly basaltic rock. Remember that from last chapter? The salts are fine-grained ferromagnesium silicates. Okay? Fine-grained ferromagnesium silicate. High iron content. Remember the bathroom tile that I had little pieces of it? I think that's basalt. Okay? Because of the high iron content, it's denser. Okay? But it's there. Thinner than the continental crust, so you're right. Bottom of deepwater horizon, yeah, you're into the basaltic rock, and then it goes on down. And when it says thinner, it's still maybe 3/4 of a mile deep. They sure didn't go that thick, you know. Anyway, I'm just sort of guessing at that. All right, here we'll see representation of it. Here is the oceanic waters. Okay, so the oceanic crust is the crust that's underneath the waters. Okay, now if you figure, this doesn't have a scale on it. If that's about a mile deep, or more, maybe several miles deep, the deepest part of the oceans are between 1 and probably 2 miles deep. I don't know, Marianas Trench, I don't know how deep it is, but it's pretty deep. But that's the depth of the water. You still have probably a significant thickness of oceanic crust. Not nearly as thick as this, but you still have it. This is basaltic, meaning it's denser than the continental crust. It's thinner than the continental crust. It's typically darker than the continental crust because of the iron content. Now, one thing that's pretty poor about this picture, we'll see it in later pictures. If this crust were doing this, it would be going underneath the continental crust, not going on top of it. Why? Because it's denser. It wouldn't climb up, it would go under. Okay? And then underneath all that, and this could be several miles down, you finally hit the mantle. Okay? And that's just the very edge of the mantle. The mantle is so extraordinarily thick. Okay? Then we have the continental crust. Most of the continental crust is granitic rock. What kind of rock is granite? There's 3 classifications of rock. Granite is not metamorphic. Igneous. So is basalt. Both of those are predominantly igneous rock. Now, what's the difference between basalts and granites? There's about at least three or four major differences between basalts and granites. Granites are basalts are fine grained, granites are coarse grained. Most of the granites, believe it or not, were formed deeper so that they cooled more slowly, and then they made their way to the surface. The basalts on the bottom of the ocean, when that magma came up and became lava, it cooled really quickly because it had water on top of it. So that makes it a fine-grained crust. Okay? That's one difference. The grain size of basalts finer than the grain size of granites. Okay, that's one. Another difference. Anyone think of any other differences? They're both igneous rocks, so that's what they have in common. So basalts are fine grained, granites are coarse grained. Any other differences? I got Steve, sir. Sorry. Say again? What's another difference between the basalts and the granites? Say again? No, those are sedimentary rocks are plastic or chemical. These are both igneous rocks. They aren't classified like that. Okay?
Intrusive or extrusive?
Second?
Intrusive, extrusive.
Okay, yeah, and that goes with the grain size. And believe it or not, the basalts are extrusive because they cool at the surface. The granites, even though they're on the surface, they cool deeper and made their way up as erosion and stuff occurs. Okay? So there is another related to grain size. This shows one of them. The salts are denser rocks, granites are less dense. Why? Two things that contribute to density. The material in the rock. What does basaltic rock have more than granite does? Iron. That's supposed to be an Iron Man. I'm not a very good Iron Man. Okay. Basalts are high iron content, granites are low iron content. That's why basalts are denser and granites are less dense. Something they have in common, they're both silicates, but these are ferromagnesium silicates, these are non-ferromagnesium silicates. This has iron content, this one does not. It does have some, but not as much. Which leads to another difference. If you have more iron, less iron, what does that create? Another difference. Color. Basaltic rocks are very dark because they have iron content. Granite rocks are very light because they're mostly non-ferromagnesium silicates. In other words, higher silica content, less iron content. Okay? And there probably are some others. Okay. Now, big messy word here. I don't know exactly how to pronounce. The Mohorovičić, or something like that, discontinuity. They commonly call it the MOHO. Thank you very much, so I don't have to try to pronounce that. That's the boundary between the mantle and the crust. That's the Mohorovičić discontinuity. Now, you might say, how do we know the mantle, where the mantle is, how deep is how thick the crust is and stuff? The seismic wave velocity increases sharply as it goes from crust to mantle, which is a weird way to say it, because most of the time the earthquakes are occurring deep, like in the mantle, so the seismic waves are traveling from mantle to crust, and then the velocity would decrease. The reason for that is the mantle is denser, much denser than the crust is, because it's had all that pressure on it. And the crust is mostly silicates. The mantle gets away from the silicates more to the heavier, denser rock. Okay? So the wave velocity relates to the density. Okay? The denser it is, the faster it goes. So it increases when you go from crust to mantle, which means you decrease when you go from mantle to crust. It's that wave velocity. So that's how we know. We see the waves coming, we measure them, and we can estimate how the thickness of the crust is. That gets to the Mohorovičić discontinuity between the crust and the mantle. Okay? Now let's go to the mantle. The mantle is the very thick shell between the crust and the core. The crust, remember, is so thin, very thin, only a few miles deep. Okay? But the mantle takes up 80% of the Earth's volume. Now notice we didn't even talk about what volume the crust takes up. It's just a thin little shell, okay? Not much there, okay? But even though it takes up 80% of the volume, it only accounts for like 2/3 of the Earth's mass. 2/3 is about 67%. So where's the rest of it? The core is even denser than the mantle. The mantle is denser than the crust, but the core is denser because you have all that weight pushing in on it, okay? So it takes up 80% of the volume, so most of the Earth is mantle, and 2/3 of the mass. So most of the Earth's mass is too, but not as big a percentage. It is composed, the mantle is mostly of olivine. It is a ferromagnesium silicate, okay, but it's so heavy in iron, less heavy in the siliceous material. So olivine is a very dense mineral that takes up, that mostly comprises the mantle. Now, have we ever been there? How do we know all this? We don't for sure. Here are our three data sources. Number one, the seismological data. We study how rapidly those waves make their way through from the site to us. The speed, that relates to the density, the thickness, and those kind of things. Now this is somewhat bizarre. How do we know about the interior of the Earth? The nature of meteorites. What? Meteorites are falling from the sky. The Earth, the mantle in the Earth is way deep down. How does that tell you? Well, if you think about it, they're all made out of the same stuff. Okay? The meteorites are leftover material from the sun's solar system formation. So yeah, they would tend to have, since 80% of the Earth's volume, 2/3 of the mass is made up of the mantle, or is in the mantle, then the meteorites are probably going to be made up of the same stuff. Okay? So the nature of meteorites, that's the data source too, though it seems a little far-fetched, but it is true. And then finally, what comes out of volcanoes? That's what's in the mantle, because that's where most of the volcanic material comes from. Okay? Or at least the edge of the mantle, or part of the mantle. Okay? Now, remember, where do we find basalts? Which crust? Okay, it's fine grained, but which crust? Two crusts. Oceanic crust, okay? Mostly. Now, we find basalts in the continental crust too, but most of those have been pushed up from previous ocean floors, okay? So, we're looking at the correlation of the basalts that we see mostly in the oceanic crust. These are close to the silicate composition, chemical composition of your stony meteorites. These would probably be more closely related, the ones with the mantle, to the iron meteorites. Remember, we had two classes of meteorites. Iron, we had stony, we had iron, and we had stony iron, okay? The iron was probably more like the mantle, the stony are more like the basalts, okay? And the basalt is the most common volcanic rock. So I would think most of Iceland would be basalts. Most of Hawaii will be basalt. They're made up of volcanic materials, okay? Anywhere you have volcanoes, you're going to have basalts there. And they're very similar to your composition of stony meteorites. And they will be, that's how we know what makes up that part of the crust. It seems like this slide should have been with the crust, not with the mantle, but we're okay. The mantle is mostly olivine, which is a much denser ferromagnesium silicate. Basalt is a ferromagnesium silicate, but it has more siliceous material even than the olivine. Now let's go to the core. Oh, we better not. It's too hot down there. Okay? The core makes up 15% of the Earth's volume. What was the mantle? 80. So what does that leave for the crust? 5%. So they didn't say that on the crust slide, but if you add the other twos up, you'll see. Okay? So 5%, even though it covers the whole outer part of the globe, it's only 5% of the Earth's volume. Okay? The core makes up 1/3 of the Earth's mass. What was the mantle? 2/3. What does that leave the crust? Less than 1%. Okay? A very small percent. Because it's very lightweight, low density, it doesn't have that much mass. Okay? It has mass, but compared to the rest of the Earth, not nearly as much. Now, the P-wave seismological data tell us much about the core. Why is that? Two reasons. First, the okay? And because of that bending, you have a shadow zone, okay? Now let's say we had an earthquake here. Let's say it's somewhere in the upper part of the mantle up here, okay? Now, you have the P waves go out in all directions. Three-dimensional, this only shows two. And you get from seismographs all around the world here, you get signals, okay? Because those P waves travel through the mantle. This is mostly the mantle. This is all the mantle, okay? Go through the mantle, the solids. However, when they get to the core, and there's two reasons for this, and P waves are what kind of waves? Name two or three names for it. Pressure waves. Second. Primary waves. Okay. Longitudinal waves. Okay. They go through liquids. But when they go from a solid, the mantle, to the liquid, they get refracted, meaning bent. They bend inward. They get to the solid inner core and get that spread a little bit more, and then come back and spread a little bit more when they reach the liquid to solid interface, and then they come out here. What's bizarre about that? Because of that refraction in here, there is what you call a shadow zone. Between 103 and 142 degrees approximately from the location of the earthquake, you don't get a signal. You get signals here, you get signals here, you get signals here, but you don't get signals there or there. And that's because of the refraction of the P waves in the core, because of that dense liquid that's in there and even denser solid, because the P waves go through all of it. Okay, now, do we know for sure that's it? Maybe not for certain, but the models that they put together, so only the best way they can come to describe this is by getting those densities, the liquid and solid combinations. That way they can come up with this model that matches what you see in reality. Okay? Now, those calculations are used to calculate the shape and the size of the core. Okay, the source of the data on the interior, this is the source of the data that we have for the interior makeup of the core. We can't go down there and take a sample, okay? We can't dig that deep, number one, and even if we could, we would have magma blowing up in our faces, so we couldn't, no way we can test it. But these kind of measurements and models to match the measurements, that's how we tell basically what's going on, okay? That's the source of our data for that. Now, that's the P waves, the primary waves, the longitudinal waves. We also have S-wave seismic data. Tell me some characteristics of S-waves and names for it. What does S stand for? Second? Secondary or shear. Another is transverse. That means the same as shear. These are waves that the movement is this way, but the wave propagation is that way, okay? Perpendicular to it. You have a larger S-wave shadow zone. Now, why do you reckon that would be true? What's true about S-waves is, or true about P waves, not true about S-waves? They do not move through liquids, so you're going to have a huge shadow zone because the outer part of the Earth's core is liquid. No S-waves make it through. And sure enough, that's what we see. The shadow zone extends everywhere beyond that 103 degrees. So the S-wave, notice they did a transverse wave here, okay, when they drew this. Still the 103 matches exactly what you saw with the primary waves, this part, but nothing makes it through, meaning that this has to be liquid. Has to be liquid. It doesn't allow any S waves to come through. So you have a huge shadow zone for your S waves, where you have the same size up here, but then you pick up P waves down here, like we saw in the last slide. Okay? The core acts like a liquid, not allowing S wave propagation. Does allow P waves, but not S waves. Now, it does have two parts, the liquid outer core, a solid inner core. You can't tell that from S waves, you can from the P waves, because if you think back on the P waves, notice how they can contract here. That's probably due to the solid inner core. It really concentrates them down, and when they get back in the liquid, they spread back out again. Okay? So, okay. This model is supported by the S wave and P wave data. Again, they feed in all kinds of different inputs to the model, trying to reproduce what we see with the actual data. This gives it to us. I don't think there's any other way they've thought of that they could come up with what the composition would be. Does that make sense? Okay. That's how we know, or the best we can guess, of what the inner structure of the Earth is. Now, other core evidence. Okay. Back to these meteorites. Man, how are we talking about the interior of the Earth by looking at meteorites? Okay? The iron meteorites, remember there were iron, stony, and stony iron. The iron meteorites are mostly iron and iron nickel alloys. We think that's the same. We don't see that anywhere else on the Earth, so we think that must be what's happening in the core. They're thought to mimic the chemical composition of the core. Because they're out there, they came from somewhere, they must be in the Earth too, and since there's nowhere we can see, we think they're in the same place there. So notice, not much silicate here. It's iron or iron nickel alloys, so it's probably pretty close to pure iron or iron nickel alloys. Some other things probably mix in too. But not just that. The Earth's magnetic field has to relate to that too. The source is the turbulent flow within the liquid core. You can't, I don't think there's any model that you can come up with to get a magnetic field unless you have a liquid core. You just can't do it because you have to have moving charges. And how do the charges move? By that turbulent flow. Turbulent flow happens in fluids. It doesn't happen in solids. Solids don't flow. Fluids do. Okay? But the material must also conduct electricity, which means it's probably going to be one of those metals. Not necessarily those, but to be magnetic, it's got to be one of those, or cobalt. Those are the only three naturally occurring magnetic materials. So the meteorite and the magnetic field data are consistent with the iron core. Okay? And again, they put together these models and match them to the field data. The only way you reproduce the field data is to make those kind of assumptions. They work, they seem to fit. They can't come up with others that do, that make sense, in context. So that's the reason we think, and we have a very good confidence that that's probably what we got. Does that make sense? Okay. Now, that was the rough thing. Crust, mantle, outer core, inner core. Let's get a little more detailed in the structure. Okay? When you see sphere here, okay, that means something that's circular, right? Or three-dimensional circular. Go and introduce a new term here, asthenosphere. I'm not sure if I'm pronouncing it right, but that's a thin, hot, elastic, semi-liquid. Oh boy, that's the thing. Elastic means that even if it gets compressed, it springs back, or if it springs, it compresses back. It returns to its real shape. It's semi-liquid, not a pure liquid, but not a pure solid either. Layer that's somewhere in the upper mantle. Okay, and that's what I was talking about before. That's what I think that little orangey thing beneath the crust and above the mantle was. This is the upper part of the mantle. Okay? Now, this picture shows, it doesn't really show the crust very much. There's the mantle, there's the outer core, there's the inner core. Okay? And it gives approximate dimensions here. I'm having a hard time reading that. You'll have to look in the book to the diameter of the radius of the Earth is about 6,370 kilometers, approximately. Okay? Now, they don't show for the inner core, but they show the mantle as being about 2,900 kilometers thick. And then you hit the outer core and then later the inner core. Okay? Now, in the mantle, in fact, in the very upper part of the mantle, and again they show this, here's, what would that represent, the yellow? So on the very top, what do we call that? Thin outer shell. The crust, that's the continental crust. Here we have, the blue is water, the oceans. What's the little dark thin thing here? The oceanic crust, there it is. You don't see much water here, but that's the oceanic crust, which is made mostly of the salt, in the continental crust, mostly of granite, exactly, okay? Now, beneath the crust, and what is the boundary there? That big word. The MOBO, okay? Motorographic discontinuity. Okay, then you get into the mantle, okay? Now, they have what they call the uppermost mantle, then they have the main mantle, the mantle continuous downward, okay? In between the crust in the uppermost part of the mantle and the lower part of the mantle, they have this another band that looks to be, I don't know if this is true, but looks to be about the same thickness of the continental crust. Now, I don't know if this is drawn on scale. That's your asthenosphere. The asthenosphere is a thin, just like the crust is thin, hot, because you have all that pressure above it, elastic, semi-liquid, okay, layer somewhere there in the upper mantle, beneath the upper mantle. And by the way, another term here, and here we have it, okay, and by the way, the asthenosphere distinguished by a sharp decrease in the seismic wave velocity. Now, when they say decrease, that's coming from below, making its way up. That's where your decrease occurs, in the asthenosphere. Okay? Now, it's semi-liquid, meaning the S waves do make their way through that, because it's not a pure liquid. It's solid enough it can, S waves do make it through. But it's, and it's so thin, it doesn't really bother much. Another term, lithosphere, that's the upper mantle above the asthenosphere and the crust. The upper part that's above the asthenosphere, which is the upper part of the mantle and the crust, that's the solid layer above the asthenosphere. That's called the lithosphere. Litho meaning rocks, basically. Remember, what was the term we used? When we talked about compaction and cementation, that was, we used the term litho in there. I can't remember exactly what term it was. Okay. All right. The lithosphere includes the entire crust, the continental crust, the oceanic crust, everything in the crust, plus, and including the boho, that's the boundary between the crust and the mantle, and the upper part of the mantle. Okay? That's all above the asthenosphere, and that's called the lithosphere. Now, that's where the plates live. Made up of rigid plates floating in the upper mantle, floating on that asthenosphere. Remember, it's semi-liquid. That's that boundary that separates the plates from the solid part of the mantle. So the plates are the upper part of the mantle, the lithosphere, and the crust. That's what makes up the plates. Okay? And we're talking about, the chapter is plate tectonics. That's what we're dealing with. Okay? Oh yeah, they do show the crust here. That little blue, this is so thin. Mantle is really thick, outer core, inner core. And the plates for the plate tectonic float on the asthenosphere, and they're the upper mantle and the crust. And they're the ones that move around. The lower part of the mantle basically doesn't move. So here's the theory of plate tectonics. The individual continents shift positions on the Earth's surface. And it's just not the continents. We'll talk about this a little bit more. They're the plates, and generally the continents make up plate, or are all in the same plate, but they are plates. The patterns between the continental shapes can be fit together. Now this was a theory long before we had plate tectonics. We didn't know why, but it was the goodness gracious. They have a name for it. Basically, the moving continent. The continental drift. There it is. The original concept was continental drift. That the continents are slowly moving apart, or some continents. The main place that happens is in the Atlantic, right here. Okay? And if you look at this, you notice how North America slopes like this, but Europe slopes like that. So it looks like they would fit together. So there's how the bulge of Africa can almost fit into the Gulf of Mexico and the Caribbean. Yeah, that's where that comes from. Where South America, the Horn of Brazil, fits up almost snugly right up into the curve of Africa. Of course, there's some various movements, some twisting as well as moving apart. But sure enough, that looks like what's happened. Okay? That was originally called continental drift. Later, when we came up with and understood enough about the asthenosphere and those other things, we said, hey, this is plate movement. It's not just drifting continents, but they're plate movements. Okay, so the individual continents shift positions on the Earth's surface. The patterns between the continent shapes can fit together. All were one part, this is at least the theory, of a single large landmass called Pangea. The Gea here is sort of the same root word that we have for geography, geology, geoscience, that's earth science, okay? So that's the Gea part. Pan means the whole. Like a pandemic is when everybody's getting sick all over the place. An epidemic is when it's a little more localized. Pandemic means everywhere. You'll see those terms. So all were once part, this is a theory anyway, of Pangea. And the original concept was continental drift. And someone came up with this hundreds of years ago, and people thought that guy was crazy. Because continents can't drift. How can they drift? They're continents. They don't move. They're fixed. But he just looked at this and said, look, they look like they were once together, and they have been drifting apart. More recently, we have actually measured that drift apart. What's more, we've actually taken video of that ridge that goes right down the center of the Atlantic, and that's where the plates are moving apart. And there's volcanic activity all along there, it's just all below the water. Except at Iceland. Iceland, it just happened to be near the surface. Lots of volcanic matter came up there. That's why Iceland is there. It's right on that mid-Atlantic ridge. Okay? We'll get there later. Now, there's more evidence that this has happened. Evidence from the Earth's magnetic field. Igneous rocks, what makes them igneous rocks? What is an igneous rock? Okay, it's formed from molten matter, okay? It's solidified from a liquid, okay? Really hot liquid, obviously. Now, some of those igneous rocks are non-ferromagnesium, right? The granites, the high silica, low iron content. But many of these rocks, basalts included, have very high iron content, okay? Now, this is stuff that was covered in the first half, but we're touching on it now too. The Earth's magnetic field, we know what it is, okay? There's an Earth magnetic pole, North Pole and South Pole, not quite in line, but pretty close to the actual North and South Poles. That's where compasses point toward. So the Earth acts like a magnet, okay? Because the Earth acts like a magnet and has these field lines, magnetic field lines, when that magma comes bubbling up and reaches the surface, it becomes lava and then solidifies. If it's in the presence of the strong magnetic field of the Earth, if it is, and lines up that way, then that becomes naturally occurring magnetic material. It's called lodestone. The mineral was magnetite. I think you saw hematite when you did the last lab, right? Magnetite has the exactly same chemical composition as hematite, but hematite is non-magnetic, whereas magnetite is naturally occurring magnets. Okay? Now, the magnetite poles are locked into alignment with the Earth's field on crystallization. Okay? So you have layers of these magnetic fields pointing toward, say, the north. Now, here's something you may not be aware of. The Earth's magnetic field varies in strength and direction over time. Now, I can't, and I don't think anyone can give you a good reason why that happens, but it does. They have documented 22 reversals over the past 4.5 million years of the Earth's magnetic field. Documented. How do they do that? They take cores down through that basaltic rock, and they find the magnets pointing this way some places, that way other, this way, that way. 22 times they've reversed themselves in the cores they've been able to take, mostly in the crust. Okay? Now, in between those layers are layers when there's really doesn't seem to be much magnetite present. It hasn't. That means that the magnetic field has weakened. Now, here's my guess, and this is just my guess. I've never seen this in the literature, but my guess, the Earth's magnetic field goes like a sine curve. There are times when it's very strong, times when it's very weak, and times when it may be opposite. Now, why would that be? I don't know, except remember they think it's from the turbulent flow. Turbulent flow meaning you have these eddies going on in there, okay? So therefore, you have situations where the eddies are more in one direction than in another. I don't know, I can't explain why, but it seems to be what's happening. So all of man's history has been in one of these periods when north has been north, okay? Somewhere in the past, if you'd had a compass, it would have pointed toward the South Pole, not the North Pole. Of course, how could you tell? You just put the point on the other end and you go with it, okay? But indeed, they have found that to be true. From the cores they have taken, through the crust, I don't know if they made it into the upper mantle or not, but certainly through the crust, where the magma and lava has deposited on the surface. Okay? Here is the representation of that. Now, I don't know if you realize this too. If I asked you to point to the north, where would you point? Anyone have an idea? Yeah. Most of the time we say that way's north. That way's pointing in outer space. North would be down that way because we're on the globe. So the North Pole would be down there. Okay. So not only if a compass needle was free to float three-dimensionally, it would float like this, not just like this. We limit it to a horizontal, so it floats like this. But if we gave it freedom, it would be like that. Okay. And because of that, we have seen the magnetite crystals preserve the orientation of the Earth's magnetic field. So this would be north. And that was north for a while, for several layers, but then sometime or another, it points in the opposite direction. Those chords that they got from this, and then they start pointing back again. Those are 3 of those reversals represented right there. Now, what I think they're probably leaving out is in between the reversals, you probably have layers that there's not much magnetism at all. Now, I don't know if this is a fact, but I can't imagine these are right adjacent to each other. I'm guessing there are layers where you, like it said, varies in strength and direction. So my guess is that in between these reversals, there's regions where you didn't have much magnetic field at all. I don't know if that's true, but that's my guess, okay? And if indeed that was true, if man had lived back then, he couldn't use a compass because there wouldn't have been a significant moving of the compass, okay? Be interesting to find out. We've been within just, how long have we been on the planet that we know of?
6,000.
Yeah, out of 4.5 million, that's insignificant, okay? So we've all been in a time period when there was, or at least as far as we know, a decent magnetic field. We haven't had a reversal in our lifetimes anyway. Okay, and you wouldn't. These probably take so long. Yes?
I got a buddy that worked in the mine. He told me that trees are like in the ground.
That what?
I got a buddy that works in the mine.
Right.
And digs shafts straight down.
Right.
He said they'll cut through a big tree, and you can still smell the wood from the tree.
Oh my goodness.
And hundreds of feet down
Hundreds of feet down.
around here. And some guys said palm trees and well, now that just didn't be that deep all of a sudden.
Yeah. Obviously, there was some pretty major sedimentation going on the top that preserved that thing. You've probably all heard of Mount Vesuvius, right? It's in Italy. It erupted and just buried an entire town, a pretty big city, Pompeii. In fact, they, as far as I know, until they excavated some of it, people didn't even know it ever existed, okay? But it was under so much lava stuff that they have dug down into that and found an entire city under there. So that probably, things like that must have happened, okay? Could it have been a huge flood type thing that covered it with sediments? Could have been that too, but that's almost hard to believe, so, yeah. If we only do it, we used to say when we first bought our first house in Birmingham, it was a 1920s house. And we found things about where they had added to windows that had been there that weren't there anymore, stuff, and we used to say, oh, I wish the house could talk and tell us all the changes that it's had and seen over the time. Well, we wish those trees could talk or thing and tell us what in the world happened back then. But if you think about it, where are the biggest oil deposits that we know of?
North Africa.
Yeah. Saudi Arabia, basically, right? And in the Middle East there, okay? What is that now? Desert! I mean, hardly anything grows there. But what made that oil? Lots of lush vegetation that got buried. So there's been some major changes over time. So yeah,
I heard people talk about how catastrophic pole shift would be.
yeah. And that's why I can't imagine if there's been 22 of these, that would be way too. So I think they've been very gradual and probably somewhat natural. Okay? I have no reason to back that up, no evidence to back it up, except the fact I can't imagine it any other way. That's not very good scientific. Not scientific evidence at all. Okay. Oh, let's see. There was an example that I sort of just skipped over. probably I skipped over way too much. Let me see. There was a table 18.1 at the top of 461, comparison of the oceanic crust to the continental crust. The age, the oceanic crust, we think is less than 200 million years old. The continental crust, we think, is up to 3.8 billion years old. Whoa, big difference. Thickness oceanic crust, I was saying a few miles, 3 to 5 miles. That's the oceanic crust. The continental crust, anywhere from 6 to 47 miles thick. That's pretty deep, and yet that's just a little bit of very thin, okay, compared to the Earth. Density, oceanic crust, about 3.0 times 10 to the, 3.0 grams per cubic centimeter, where the continental crust, which is mostly granite-type rock, 2.7 grams per cubic centimeter. Basically, that's going to be our next lab, is taking densities of different types of igneous rock. And the composition, oceanic crust, mostly basalt, and the continental crust is granite with some schist and gneiss. Okay, gneiss schist, okay. Granite being what kind of rock? Say again? I can't hear it. No, granite is igneous, and so is basalt. Schist and gneiss, though, are mostly the third type, metamorphic. Those have had lots of heat and pressure that change the crystal structure. Okay? Now, example 18.1, let's see if it's worth looking at. What is the height at which the oceanic crust floats in the mantle? Assume the average oceanic crust thickness is about 7 kilometers, which would be 4.5 to 5 miles. Okay? The height of the crust floating above the mantle is equal to the thickness of the crust minus the thickness times the density ratio. I'm not even sure what they're asking for here. What is the height at which the oceanic crust floats in the mantle? I'm not sure I even buy their question or rationale there, so we won't go into that. What is the height at which the continental crust floats? Okay? And you see there's a pretty big difference there in those two answers. I'm not sure I understand what it's talking about. Oh, okay, I think I do know. Okay. If you have a asthenosphere, that's the semi-liquid thing, and the crust is floating in it, which it really isn't. It's the upper mantle and the crust. So it's sinking down some, and that's what they mean. How deep is that? Okay. Again, I think it's a pretty poor question. Okay. But then on the top of page 464, seismic tomography. Have any of you ever had a CAT scan? I'm not sure I have. I've had a couple of different kinds of scan. I don't think any of them have been CAT scan, but they're very similar. What it is a common diagnostic imaging procedure, combines the use of x-rays with computer technology, and it stands for computed axial tomography. Tomography means drawing slices, okay? And that's what the computer does. I do know at one time, I think it's happened maybe 3 times in my life, I've had what they call a heart flutter. It's not a fibrillation, but it's a flutter. Rather strange. I can just suddenly feel not suddenly, but I feel my heart beating, which I usually can't. I know it's beating, I'm still alive, but I don't feel it, but I can feel it, and it's rapid and a little irregular, and I can just sense it's going on, but I don't feel anything different except I can tell it's beating. And one time, the third time it happened, I happened to be at a doctor's office when it happened. I described it to doctors and they got all woo, but this was the time I was there, and they sent me up to a cardiologist, and he studied the things and said it wasn't fibrillation, it was a flutter, and he explained the difference to me. But what he did, actually the time before that, he had me on the treadmill and doing, going faster and faster and all sorts of things. I was not having any problem at all at the time. And finally they said, okay, inject the dye. So they injected the dye. I went for a little bit longer. Then I rested for a while. And then they took pictures. And the pictures actually, virtually, they didn't really, slice my heart this way and that way. All three different ways. And he looked at my heart and said, perfectly fine. Now you couldn't ask for a more classic picture than this. Everything looks good. He said you have a flutter, not fibrillation that would cause some other problem. So it wasn't quite a CAT scan, but it was similar to that. It computer generated slices. Okay. Well, a CAT scan applied to the Earth's interior is a seismic tomography procedure, tomography procedure, and that's a really interesting read. So I would suggest taking a look at that. Okay. And the rest of these we've seen. Okay, now we're getting to this part. Okay, I think we talked about that slide. Here is evidence from the ocean. So we saw evidence from the plate tectonics, from the Earth's magnetic field, you've read and studied in its deposits. Now let's look at what we know from the ocean. From the ocean, we know we have these ridges. Now, why would we have these ridges? They've studied them. They've taken soundings and mapped the bottom of the ocean. They can't go down there, but they've mapped it with taking soundings and stuff. And they sure enough, there are ridges in the middle of the ocean. Okay? These coincide with measured submarine, that means below the surface of the ocean, earthquakes. They've known they've happened. They've measured them. They've recorded them seismographically. And what that makes is a rift along the crest of those ridges. Okay? Large amounts of heat escapes from that crest. They've measured water temperatures at that. They know the heat's coming from there. And the biggest one of these is called the Mid-Atlantic Ridge. That's the one I was talking about. It goes right down pretty much the middle of the Atlantic Ocean. Okay, it goes right through Iceland. Iceland is one of those volcanic islands that came from that. And it goes down and, it's not a smooth thing. In fact, I can't believe it's that sharp an irregularity. I think it's probably smoother than what they show here, but right down the middle of it. Okay? And what's happening there is volcanic activity coming up because the crust is thinner right along that ridge. Okay? We'll come back and give a name for that later. That's called the Mid-Atlantic Ridge and the Rift Valley. On either side of the ridge in this depression, which is sort of like a valley. Now, not only do you have the ridges, you have trenches. Long, narrow, and deep troughs with steep sides, and they always run parallel to continental edges. Not here, and not here, but over here, and on the backside. And sure enough, when I was in the Navy, we went out of San Francisco. My home port was Concord, California, which is inland from San Francisco. We came up out the Sacramento River under the Golden Gate Bridge and made it into it. And sure enough, with soundings, you'd have rocks and stuff, and suddenly the bottom just dropped out. Okay? And it would go really deep, and then it would come back up. That's what we meant by oceanic trench. Long, narrow, and deep troughs with very steep sides, always parallel to the continental shelf edges. And that's why if you go to the West Coast, you don't have the beaches you do on the East Coast and in the Gulf. Actually, I've been on Virginia Beach before, and you can sometimes walk out almost out of sight and still find sandbars. You try that here, you're down, okay? It's deep, it's abrupt. Very different, the coast on either, the beaches on either coast, okay? What we call it here is a continental shelf, here is a trough, okay? Okay, so that's what we have. They don't show the troughs here, the trenches here, but they are there. In fact, a lab that we'll do, probably one of the last labs we do, you'll look up those things. Now, where does that come from? Well, here's the hypothesis. Part of the plate tectonic theory that the seafloor is spreading in certain areas. How do we know? Hot molten rock moves up from the Earth's interior, emerging along that rift, and the outflow is in both directions, and it creates new rocks on either side of that ridge. And they're constantly forming newer ones and newer ones, so the deeper you go, the older and older the rocks are, okay? We have drilled, not just there, but also at the edges of the continents. We drilled down there where the oldest rock should be, with other rock on top of it. And the drilling evidence shows you have thin sediment layers near the ridge, becoming thicker as you move toward the continents. Let's get a picture of that. Okay, this isn't quite the picture you want, but the middle part here, now when you say new, 0 to 5 million years, that's new geologically, okay? 5 million years, we have been here a few thousand of those years, and that's all, folks. So the Earth is very old compared to us. 0 to 5 million years there. The next, on either side, we have 5 to 23 million years. On either side of that, 23 to 38 million years. On either side of that, 38 to 53 million years. On either side of that, 53 to 65 million years. And then, real close to the edges there, 65 to 135 million years. Still pretty new, folks, geologically, especially if the Earth's been around, what is it, they figure 4.8 billion or something like that, you know, what's 135 million compared to that? So this has all been, quote, fairly recent, you know, geologically. I mean, we didn't exist but a little bit of that time. That's why people say, how could they be drifting? You don't notice any. But sure enough, nowadays, they can do very detailed measurements between the same 2 points, and they do find it's like a fraction of a centimeter a decade or something like that, but they are moving apart. Okay? The newest, thinnest layers of rocks are in the middle, and the further you go out, the more layers you find, and the thicker layers you find. Okay? So the thin sediment layers are near the ridge, becoming thicker toward the continents. The older fossils and rocks are near the continents, newer, younger things near the rifts. You don't find any old fossils here. And you find tons of them here and here. And as you go out, you get older and older until the oldest are there. You come in this way, you get nothing old, only recent things toward the middle. And they can date those fossils too, you know, carbon dating. It's not precise, but it gives them a real good idea. Okay? And that's why you find absolutely no new stuff, old stuff near the center, and lots of old stuff near the edges. And it grades that way. All right. And then we were talking about the magnetic layers that we have, the magnetic seafloor spreading evidence that we have. Okay. When you see the term paleo, now there's a diet called paleo, which I think takes you back to the Stone Age. No, I think that's what their idea is. This is how people really develop. So you need to go back to this. But these mean very old magnetic patterns that you do see in the magnetic strips on the ocean floor, basaltic rocks. You know, the iron rocks that form the magnetite layers. Okay? Identical magnetic reversal patterns on both sides of the ridge, and you have fewer and fewer as you get closer to the ridge, more and more as you go down, but they're identical on both sides. So you know those were formed at the same time, but these weren't even there at that time. So you can do the patterns match those found elsewhere, providing age determination. Okay? So not just relying on fossils, but also the number of reversals you see as you go down. Okay? Remember they said 4.5. I think they had that wrong. When I saw it, I thought it had to be wrong. Let me scoot back here. When it says 22 reversals in the last 4.5 million years, I have a feeling that should be billion, but let me see. No, they say in the book million years. 22 magnetic reversals in the last 4.5 million years. Basically, 4.5 million years. That would all be within the screen zone, okay? So I think there's something a little fishy there. I don't see that the timeline lines up properly. That's just me though, so I don't know. Okay. Okay. Here's another illustration of what they're saying. And for the life of me, I can't figure out why they show these as vertical layers. I would be showing these as horizontal layers, not vertical layers. I think the drafting people got it wrong. Long time ago, there was just one new rock in the middle, and then another came and pushed those out, then another. See, I think these should be going on top here, not vertically, sort of horizontally. And then another, and then another, and then another. It's pushing further and further apart, so as you drill down here, you get older, not quite as old, not the very newest, then older, oldest, okay? So you see the same pattern on both sides of the ridge, okay? And again, I wish those were horizontal, not vertical. Now, let's look at the lithosphere plates and the boundaries. This is on page 467, is where the book starts here. This is the basis of plate tectonics theory. That you have in the lithosphere. Someone tell me what the lithosphere is again. What makes up the lithosphere? The upper mantle and the crust. Precisely. Upper mantle and the crust. What does the lithosphere float on? Say again? An A word. A asthenosphere, exactly. Okay? Anything above the asthenosphere is the lithosphere, and it's made up of the upper mantle and the crust. So the lithosphere is broken into fairly rigid plates, and the plates float around on that asthenosphere. Now they don't float fast, they don't float much, but they do move on the asthenosphere. The earthquakes, the volcanoes, and the other rapid changes in the Earth's crust occur mostly at the plate edges. That's why they occur there, is because you have a break, you have a discontinuity there, and that's where the earthquakes occur, that's where volcanic activity occurs, and other rapid changes. Now what is an earthquake? Okay, an earthquake is when one plate is trying to move past another plate, but the edges are jagged, they're rough, they're miserable. They have big boulders sticking out on them, they get hung up, but the pressure is there. And then suddenly something breaks, that's your earthquake. Where did they have an earthquake this week? Anyone here?
Northwestern states.
Yes, Montana had one. Not a huge one. 5.8, which sounds fairly significant, but they said as far as they know, no major damage or injury. Okay? So it may have been very, very deep. Now that's sort of unusual to have an earthquake that far inland, without any other thing. There's certainly no plate boundary there. Yeah.
I've heard of earthquakes happening because of what's the gas?
The fracking?
Yeah, fracking.
may have had some fracking around Montana, I don't know.
They got a lot of fracking.
Oh, they do?
Yeah.
Okay, I know Oklahoma has had, they used to register a few minor quakes a year. Now they are averaging several minor quakes a week or a month. I mean, it's just amazing the difference. And that's from fracking. Now that is small scale stuff. That's nothing like what we're talking about here, okay? It's just minor, sort of like burps or things like that, okay? But the earthquake is where there's sudden giveaway of something. Volcanoes are where the magma makes its way through the boundary area, okay, and the other end. Now, there are 3 plate motions we deal with. I don't know, did anyone read or hear, or was there a movie on the Divergent series or something? That's not what we're talking about here. But there's diverging plates, meaning plates pulling apart. There's converging plates, which mean plates moving together, and there's transform plates, which means they're sliding past each other to some extent. Pulling apart is divergent, coming together is convergent, and moving past each other is transform. Now we use the same 3 words when we talk about the boundaries. Right now we're talking about the plate motions, okay? Later we'll talk about boundaries, we'll use the same 3 words. Okay. Here is that picture I think we saw at the very beginning. We see it again. Some of the big major plates. And notice they're not strictly continental, though they sort of are, mostly, kind of, okay? All of North America is in one plate, okay? Even including Greenland, even including Iceland, and much of about half of the North Atlantic, the Caribbean, okay, not the Caribbean down here, but I mean Gulf of Mexico, a little bit of the Caribbean. But look at this. Now this, I almost guarantee you it's not a nice smooth line like this. There is not a nice smooth line that separates the North American plate from the Eurasian plate. I can hardly believe that part of Siberia is on our plate rather than on the Eurasian plate, but they indicate it is. The main reason to support that is the Japanese islands here. That's the arc island chain, which means that is a boundary. But they don't know where the boundary goes up here. So they just drew a line there to it. It looks like to me the biggest plate is Eurasian. Europe and Asia are really on the same plate. This part is Europe, that part is Asian, but some of Asia is on ours too. Okay? But some of Asia is also on the Indian-Australian plate. Because India is part of Asia, but it's in the Australian plate. There is a boundary between those. Okay? Africa is on its own plate, but that plate includes about half of southwest of the southeastern Atlantic, okay, and a fair amount of the Indian Ocean as well. The South American plate, the border is right at the west coast of South America, but goes as far east as the central part of South Atlantic, okay. The Pacific plate is a huge plate, but it's not all of the Pacific. There are other little plates in there too, like the Australian plate, the Filipino plate. Part of the North American plate includes a little bit of the Pacific. The Caribbean plate is a little bit of Pacific, a fair amount of Central America, and a lot of the Caribbean Ocean. And then there's this Nazca plate in between the Pacific plate and the South American plate. And there's, up here is the smallest, tiniest little plate called the Juan de Fuca plate. It's just a tiny little island of a plate, you know. It's really small, and yet a lot of activity goes on there. They have the Antarctic plate down here. Now, it looks huge here, but that's because they spread the globe out, but it really is not that huge of a plate. And then they have, I don't know what this green area is. I've never seen that identified. There must be another little minor plate there, but as far as I can tell, they don't even have a name for it. Arabian plate that's here. They didn't name it here. Oh yeah, there it is, Arabian plate. Okay. But they don't have a name for this one. I don't know what that is. Okay. Now, that's generally the boundaries. Now, what kind of boundaries are they? In the Mid-Atlantic Ridge, it's the divergent boundary, because these plates are moving apart. Guess what? The Earth isn't getting any bigger, right? So if these are moving apart, something else has to be cramming together. And these are cramming together. This plate's moving this way, that and that way, so you have some pretty major problems in here. The plates are converging there. Converging kind of here too. Though some of this is transformed. Converging a little bit here. Now they don't show the arrows, but they're converging here too. So you have a lot of converging plates. There's some other plates where they are diverging a little bit. Not just as Mid-Atlantic, that's the major one. But there are some other places you have these divergent boundaries. And
the ring of fire.
yes, that's exactly it. I was just going to say that, but good that you brought it up. Around the Pacific, they call this the Ring of Fire, because these islands in here, New Zealand, these are all volcanic islands, and that's where the Ring of Fire comes from. The Aleutian Islands, Ring of Fire. The western coast of the U.S. and South America, lots of volcanic activity there. Mount Shasta, Mount Hood, Mount Rainier, all those are volcanic mountains here, down here, most of the Andes, volcanic mountains. Why? Because you have all this plate movement going on there. So yeah, that's why the Pacific, because the Atlantic is spreading, the Pacific has to be contracting, and where you have that, you have problems. And that's the Ring of Fire is evidence of those problems. Now, it doesn't really show the transform boundaries well here. We'll see those on other slides. They're mostly showing converging or diverging here. But you do have transform where they're sliding past each other. Okay. I didn't think to ask, do we need a little break? Yes. You do? Okay, I should have when Ricky got up. I'll wait till he comes back to give him a break. Sorry about that. But let's do a very quick break. And when we come back, it'll be basically about time for roll call again. And then we'll just wrap up what we're going, which is really easy to do, but I'll wait and see if he comes back. All right, so I think we beat that slide to death, didn't we? I was looking for transform boundaries here. They don't really show them well here. I think you'll see better pictures later. Most of these show converging and diverging, okay? And they don't even show them diverging that much, but they do have them here. Okay. So let's look at these three, starting with diverging boundaries. These occur between two plates that are moving away from each other. Guess what? If plates are moving away from each other, there's an opening in between, isn't there? Now, not a huge opening, but just a thin place where molten material from the mantle rises to fill the fissures. Now, we don't think of there being much molten material in the mantle except around the asthenosphere, because the mantle is solid, okay? So, where would the molten material come? Mostly from the asthenosphere. Remember, it's semi-liquid. Okay, so it comes up and fills the gap in between the moving plates. Now, that forms new crust, and we call those regions around there the new crust zones, because new crust is constantly being formed as that magma comes up, often accompanied by volcanic activity. Think Iceland. I think I've told you before. Iceland heats itself with geothermal heat. They don't have to burn coal. They don't have to do anything else. They just pump water down on the near the volcanic rock. It gets hot. They pump it up and pump it into people's houses. Just water, and they heat very cold area, and they heat, do all their heating with geothermal, which is a great way to go. Most of us don't have that luxury, okay? So often accompanied by volcanic activity. Now, a lot of those volcanoes are underwater, you never see them, ever, but they're always happening. The Mid-Atlantic Ridge is the classic example of that. So here we have the diverging plates pulling away from each other. That means magma from the asthenosphere. Now this, okay, catch this. Here's your crust, and this is under the ocean here, so that's what kind of crust? Oceanic crust. And what would it be made of? Mostly basalts, which are, give me some characteristics of basalts.
Igneous.
Say again?
Igneous.
They're igneous rock, absolutely. Fine crystal sizes or grain size, okay, or fine grained. High iron content, because this has lots of high iron down here. The low iron content is mostly on the continents. This is beneath this. So this is the crust. There's the lithosphere where they're pulling apart. The lithosphere is a little thinner. So here's the asthenosphere where the magma lives, okay? Semi-liquid and stuff. You reduce the pressure, and here it comes. And all along this ridge. Now, I don't know if I can catch it back again. One of the early editions of this book, the CDs that they sent with it, actually showed this boiling out of that ridge, okay? It was actual footage taken by underwater camera. It was remarkable seeing that just stuff bubbling up and then very rapidly changing to rock because of the cold water that it hit. It was just amazing. The newer things don't have that, but I think I'm going to see if I can find it again. This is about 100 kilometers thick, okay? This would be about the thickness of the lithosphere, which is made up of the crust and the upper part of the mantle. Then you have the asthenosphere, and the lower part of the mantle is on below that. So 100 kilometers is about 60 miles down. That's the thickness here. Of course, in here it's much thinner, and that's why you have the magma coming up in the fissures. And that's why you have the ridge here, because it comes up and spills over, comes up and spills over, the ridge builds and builds. Only one place I know of on that, and that's Iceland, where it's actually broken the surface. Okay? Let me go on and mark the roll again. It won't take long. Ricky's here, Amber's here, Brian's here, and James is here. Good deal. Okay. Now let's look at convergent boundaries. These are boundaries where the two plates are moving toward each other. Okay? Can you imagine these plates colliding? What's going to happen? Second? Mountains, you got it. Where can they go? They can't go down, they've got to go up. Now, let's go back here again. I told you this was a converging boundary. Does anyone know what mountains live north of India? Say again?
Everest over there.
The what?
Himalayas.
The Himalayas, exactly. The tallest mountain range in the world. Guess what? They're still growing because those plates are colliding. So that is why the Himalayas are there and so big. Okay? Now, to a smaller extent, the Andes are probably growing because the Nazca plate is, we're going to talk about this later, subducting under the South American plate, pushing up the South American plate. So that's why the Andes are still growing. To a smaller extent, this is called the Cascades here, and the Sierra Nevadas, and then later the Rockies, they're still growing, okay, because of this movement. We'll talk about some of the rest of those later, okay? So that's where the, on the wrong slide now. Let's go back to where we were. Okay. The old crust, it says, is being destroyed in the process. Sometimes. That's when the oceanic crust goes underneath the continental crust. This crust is being destroyed. It goes deep enough, it goes back and becomes molten rock again. That's what it means destroyed. Where the Himalayas are, it's not being destroyed, it's just raising up. Okay. But some old crust could be destroyed. This is called the subduction zones. Now, I used that word earlier, I forgot it was on this slide. That's the belt with one crust going underneath the other. Now, that happens when the oceanic crust goes under a continental crust. Remember that figure I showed you before that showed the oceanic crust crawling up this way? I said that was wrong. They go down. Why would this oceanic crust go underneath the continental crust? Can you think of a couple reasons? Oceanic crust is made of basalt, and the continental crust made of granite. What's one of the differences between basalts and granites? There's several. Density, for sure. The oceanic crust, the basalts are high iron content. They're much more dense than the continental crust, so therefore they go down, pushing the continental up. Not maybe too much, but some. And that's the belt for one crust. Usually the oceanic subducts under the other, usually the continental. The subducted material partially melts, joins the mantle, and it's no longer crust. Okay. Now, there are three possibilities. What I've been describing has mostly been converging continental and oceanic. Oceanic subducts under the continental. What also can happen is converging oceanic plates. Okay, that's all under the water. One of them gives way. I don't know what determines which one goes under. One subducts under the other. They're both basalts, but one subducts under the other. The Marianas Trench is one such area. It's subducted, drug some other down, that's what makes it a trench. And then the other converging plates are continental, that's the Eurasian plate hitting the, Australian plate hitting the Eurasian plate, the Himalayas are growing. So that's what's happening there. Converging continental plates, the movement is up. Converging oceanic plates, one goes down, okay? And the oceanic plates, continental plates, almost always oceanic goes subducts under the continental. That's why you have those trenches along the west coast of South America and North America. Big trenches. Okay, so let's look at the ocean continental plate convergence. I already talked about it. Let's do the slide on it. Oceanic plate is a denser basaltic material subducted under the less dense granite-type continental shelf, and therefore is marked by here's the oceanic crust. This is a converging boundary. They're coming together. What is going to happen? The oceanic goes down, and the continental rises above. Is that a smooth process? No way. That's not just nice, smooth. Let's just go under each other. It is a lot of friction, a lot of resistance. And as that friction occurs, that heats up the rock that's already hot because it's down here in the mantle, really hot. And that extra heat, it melts some, and there comes volcanoes. And that's why all along the Pacific coast, Mount Rainier is inside of the ocean. Okay, Mount Hood inside of the ocean. Mount Shasta inside of pretty much inside of the ocean. Mount St. Helens inside of the ocean. They're not right on the ocean, but they're somewhere in here, and just depending on how far down that occurred, then that volcanic material makes its way up, and that's why you have the volcanic coastal mountains and volcanoes there. Now, I think this is smoke coming out of that volcano. Actually, some of the time, when I first looked at it, I thought they showed a crater lake there, which you have that too. Okay? And what you have is that trench right off, like I said, when you went out of San Francisco Bay, into the ocean, you notice your depth went way down and then started coming back up. So there's a huge trench there right at the, they call it a continental shelf. It's not much of a continental shelf there, but a little bit. Marked by oceanic trench, deep-seated earthquakes, and volcanic mountains occur because of those. Ring of fire, like you were saying. And the example is convergence of the South American plate with the Nazca plate. This would be the Nazca plate, this is South American. Then this ridge of mountains would be the Andes. And they do go right up. Peru, Chile, high mountains right off the ocean, okay? Even Ecuador, okay? Ecuador sitting right on the equator, you go up in no time, and it's very comfortable temperatures. You would think it'd be hot and humid. No, high enough elevation, very comfortable temperatures. More like Hawaii, and probably maybe not even as warm as Hawaii. Okay. Now let's look at ocean plate convergence. The trench and underwater ridge created by subduction is associated with, again, deep-seated volcanoes. Now, in the next chapter, we're going to talk about what we mean by deep-seated volcanoes rather than shallow volcanoes. Hang on to those notions. We'll talk about those later. But when you have ocean plate convergence, one going underneath the other, then you have these deep trenches, like the Marianas Trench and others, but you also have the island arcs that form, basically, they mimic the border of those plates. The island arcs form where the melted subductive material rises above sea level through the overriding plate. There's a bunch of volcanoes under the water you don't see happening, but those that make it to the surface, then those make the islands. And here's the illustration of that. One oceanic plate subducts under the other oceanic plate, and why I'm not sure which one hangs on first, but this one doesn't rise too much, but in a sense it does, because this oceanic plate going under gets down here, so where it's so hot it begins to melt. The molten and the friction and everything else you have here melts the rock, making magma. It makes its way up through the crevices there, and sometimes this is all beneath the ocean, sometimes it cracks the surface, and that's where you form your islands, and most of these form arcs showing the boundaries of those plates. Okay? Okay? Associated with deep-seated volcanoes, really deep volcanoes, the island arcs from the melted subductive material. Okay. Now, just want to show you what we're talking about, though we don't have lots of time. And again, think ring of fire here. Okay, so we're going to look mostly at the Pacific. Here is the Japanese islands. That's the boundary of the Eurasian plate and the Pacific plate. That's why they're there. Okay. The Aleutian Islands. Look at that arc. Okay, that's why they're there. That's an arc island chain. Now the Hawaiian Islands are sort of like that, but there's no big plate boundary there. It's sort of a mini boundary, you might say, just a weakness there. New Zealand and its islands, that's an arc. Indonesia, look at that, and it stretches on up to the Philippines. The Philippine plate and the Pacific plate. The Philippine Islands are the result of that. Okay, ocean convergence. Like I said, the Indonesian islands here, look at this one. Another, this is the India-Australian plate. The boundary between that is Indonesia. Okay, and this, the Malay Peninsula, the islands of Indonesia going all the way out here. Look at those arcs that are formed. And then you have other little arcs down here. In fact, most of these islands, here's the Marshall Islands. Somewhere here are the Marianas Islands. That little island chain, and again, this is not a plate boundary per se, but it's a weakness there, the deepest ocean trench is right there. I think on the outside, the eastern side of that Marianas Island. And then the Caroline Islands are here. Just you see them all over the place. The Kiribati, the Line Islands, here they are. From the Hawaiian Islands, they just continue on up here. See, there's a whole string of islands here. Midway. I can't see the others that I know. Lake Island is somewhere in there too. I just don't see it. And Guam is over here. In one of these islands here. I can't find it now. But you see all these island arcs here. They're showing boundaries between either big plates or minor pieces of the plates. Okay? Japanese islands are one arc island plate. Continent plate convergence, the less dense granite type materials resist subduction. They aren't going to go down. They really can't. There are continents here. So they collide and the plates pile up, producing deformed and thicker crust of the lighter materials. Okay? And this is why, in fact, this is my guess of why you had the earthquake in Montana, because the subduction you had way out here in the Pacific, it didn't form something there, something gave way over here in Montana, okay? And Montana's right in the Rockies, okay? The Tibetan Plateau and the Himalayan mountains, that's where these things are growing. And that's why, if you've remembered, in the last, I would say, decade, I've heard of several really major earthquakes in this part of China, because that's where that plate convergence is going on. You see here's the Himalayas there, and they make almost an arc here, where this plate is cramming into that one, and therefore you have a lot of volcanic activity and earthquake activity here in southern China, southwestern China here, and in Tibet and those other areas. It had some pretty major quakes in the past in Pakistan, this is Afghanistan here. This is some really rugged territory there, and they have had quite a few. And here is the Arabian plate. Look at this edge here. A bunch of mountains in here too. Not a major set, but that's coming from convergence there. Down here as well. And here, almost nothing. A little bit of bridges. Okay? So you can account for most of what the features you see on the Earth's surface by this kind of stuff. Okay? The continental lithosphere, hitting another continental lithosphere, has nowhere to go but up. Okay? Because it's convergent. It can't go anywhere else. So those mountains are growing. And the Himalayas are growing. The Rockies are growing. The Sierra Nevadas are growing. Okay? The Appalachians are shrinking, okay? They're eroding away. They're not really falling, but they are dissipating faster than they're growing. Now, let's look at the transform boundaries. Transform boundaries are when plates slide past each other, occur when two plates slide by each other. The crust is neither created, like it is when you have divergent boundaries and new magma comes up, nor destroyed, which you have when you have subducting plates in this process, but there are irregularities in the movement along the boundaries because they're really rough and jagged and they get hung up easily. So the pressure builds and builds and builds, and then you have a sudden jerk. And let's not talk about any body in particular, but a sudden jerk produces the earthquakes. Okay? Now, obviously, a few times they've waited too long. And there's been pretty major obstacle. And then when there was a sudden jerk, it was really, really massive. Okay? The example of this is the San Andreas Fault along the California coastline. And this just has lots of activity along it. There was a major earthquake in San Francisco about 1900s or so, 1890s, 1900 something, really major earthquake there. There was another one. It was the World Series quake. I don't know if you remember that. Oakland was playing San Francisco in the World Series, and they had a major earthquake. I think at the time one of the games was going, maybe not the game was going on, but it disrupted things like crazy. The Bay Bridge Tunnel that goes from Oakland to San Francisco through Yerba Buena Island, that's the tunnel part, and then the bridges across the bay, they're built on top of each other, and one collapsed on the other when that earthquake occurred. Pretty major damage then. Within a few years of that, Los Angeles had a major quake, and there's all the time. They far prefer lots of little quakes than a long time between quakes and then really big quakes. They're going to happen because those boundaries are always moving. Sometimes they get hung up, and the longer they're hung up, the more major the quake is. So better to have lots of little ones than a long time between big ones. Okay? Now, what's our present day understanding here? So a major remaining question, what drives these plates? I mean, why are they moving? You would think they'd be happy just to sit there, okay? Because there's a lot of energy being wasted when they collide with each other. Why don't they stay still? Well, there's several working hypotheses. The one they're talking about here is convective cells in the asthenosphere. So what that means is, y'all know what convection is? Have you ever watched water boil in a pot? It starts in the middle of the hottest part, and it does like this. When it gets here to the top, it cools and goes down the side, which is cooler. In the middle, right over the heat, it rises up. That's convection, okay? The old radiators they used to have in school, they usually put right near the windows. Cool air goes underneath them, that warms it up and goes up. So you have constantly flow like that, okay? That's convection. So what they're saying here, convective cells in the asthenosphere. The asthenosphere is down here, and where you have maybe a real hot area, then that comes toward the surface, and then it cools and goes down. That may be what's pulling the plates apart. That's what theory, okay? The hot fluid materials rise at the diverging boundaries. Some escapes to form new crust, that makes its way to the top, but the remainder spreads the lithosphere, dragging the overlying plates with it. Now, the problem is, where's the evidence? Okay, show me the money. Show me the evidence. You just don't have a lot of it. There's another theory they don't mention here, and that's the drag of the pull that's here. This subducted plate then is pulling the rest of the plate, making on both sides here, and then pulling it down, that leaves a thing there. Maybe they work together. I don't know. Here's the picture of the convection a little bit better. The core, for some reason, a little bit hotter here, it rises and does this and pulls the plate apart. Or the plates naturally pull apart and leave a gap in the middle. There's lots of possibility. No one knows for sure. You can't really get down there and collect very good data, okay? So these are all hypotheses, not even theories. The whole plate tectonic theory, that's a theory, but these are hypotheses of why in the world this is happening anyway. You would think they'd just be happy just to sit there and not really have so many problems. And probably they don't have that many problems. Okay, guess what? We did finish the chapter, okay? There's example 18.3. If the distance between the Tal and the easternmost point in Brazil and Mount Cameroon in central West Africa is about 5,000 kilometers, how long did it take for the southern Atlantic Ocean to open if the average rate of spreading is about 2.5 centimeters per year? I've been wanting to know that for a long time, haven't you? It's an interesting little problem. You can follow how they do it. That's fine. If the distance between the Puerto Puerto Deseado in the southeastern coast of Argentina and Cape Town, South Africa is about 6,900 kilometers apart. How long did it take the southern Atlantic Ocean to open if the average rate of spread has been 3.25 centimeters per year? And both of those answers are in the order of 10 to the 6 to 10 to the 8, well, closer to 10 to the 8 years, which is 1 and 8 zeros. That would be 100 million years. Okay, quite a while. Okay. Measuring plate movement, there's a closer look at the top of page 469. That's a pretty interesting read there as well. Okay. There's another example, 18.5, earthquake data from the subduction zone is shown in the following table. What is the average slope of the subducting plate in meters per kilometer? And again, it's sort of a made-up problem, but it's sort of interesting to look at. So I'll let you take a look at that if you're interested. And then there's another one, 18.6, is earthquake data from a subduction zone, different data, and see what you got there. And it's about 360 to, well, around 300 meters per kilometer, approximately. Now, myths, mistakes, and misunderstanding. This book likes these. Bye-bye, California. You know, some people have said, why doesn't California just break off and fall into the ocean? We'd all be better off. No, we wouldn't, but it's not going to happen because that's a transform boundary. It's not going to fall into the ocean. That would be a divergent boundary. Then you'd have, So, but no, it's not going to happen anyway. That's not what happens. Earthquakes is not when the earth opens up and people fall in. That's the movies. That's not real, okay? That is made up, okay? Fiction, okay? Now, there's people behind the science. There's a good little blurb here on Henry Hammond Hess. Quite alliterative his name was, wasn't it? He lived from 1906 to 1969. 69 was the year I graduated high school, believe it or not, okay? So he only lived to be about 63 years old, too bad. He was quite a scientist. He actually measured, did the soundings of a lot of the data that we currently now have to support plate tectonic theory. He was a naval officer, I think they said, during World War II, but he served mostly scientific research vessels, and going out measuring the ridges and everything else. Interesting blurb there. This can't be your source if you choose to write on him. I think only one of you hasn't written the paper yet, which is far better than any other class I've ever had. So that can't be your source, but that can give you the idea of where to go for your source. And they talk here about ridge push, and someplace else they talk about I don't see the other one, but it's the slab pull. Okay, they don't have a picture for that, but it's the same. So two other theories that they have are hypotheses. Then there's a really good blurb on geothermal energy, which is talking about the various sites in the U.S. that actually use this as a form of energy. The more we can do, the merrier, because this is non-polluting, fantastic, renewable energy, okay? Costs you almost nothing. It's just harvesting the energy. It's already there. Well worth a read, and you can think through the questions they have there. Okay? Oh, here, figure 1820 is your slab pull theory, okay? Or hypothesis. So they showed three: the convective hypothesis, that was 1818, the ridge push hypothesis, which was 1819, and the slab pull hypothesis, which was 1820. The reality is probably some mixture of all those, possible. Okay, a science sketch, they talk about new earthquakes and volcanoes. You could probably do that. Nothing, as I say every time, replaces reading the book, reading the chapters. So please read it. This is one of the shorter summaries because this is one of the shorter chapters, and but it is a good summary. Has a lot of italicized words, those key terms, and there's probably a short number of key terms as well. But they list them alphabetically. They give the page numbers where they're first identified, defined, or described. And then applying the concepts, even though it's a short chapter, 52 questions is probably a few more than average. So best things I think to study for the test would be that applying the concepts, the multiple choice questions there. You won't see the same questions, but you'll see questions on the same content. So if you know those, you got a good job. Questions for thought, 16 of those, maybe a few fewer than normal, and for further analysis, 4 of those, so a total of 20. You'll hear me mention those again, okay, so pay attention to those. In fact, if you want to start on that, you got a weekend coming up, that's going to be part of your lab. Answer 15 or more of these 20 questions. That's the questions for thought, 16, and for further analysis, 4. Answer any 15 or more of those. That will combine with what we actually do in the lab, which is a total of 10 points there, plus 15 will give you 25. So if you want to get started on that, guess what? That's part of studying for the chapter. So I would do it before rather than wait till after you take the test. I want you to do it before so. Okay? The parallel exercises, the group A have answers in the back if you have one of these big books. If you don't, then you don't have those, but you don't have to do those, but you can certainly do it if you want to.
Did you say 15 or more of the questions for thought?
15 or more of the question is, there's 16 questions for further thought. I think that's how it is. No, for questions for thought, 16 of those, 4 for further analysis. So a total of 20 questions there. Do any 15 or more of those 20 questions. You can do all of them questions for thought, or some questions for thought, some for further analysis, however you want to do that. Now, why do I say 15 or more? Well, what if you get some wrong? If you do 15 or more, if I get 15 points worth out of there, you get 15 points. Even if you missed a couple, if you did a few extra, you may still get your 15 points. So 15 more, and like I said, it's a great study guide too, to study for the test. Okay. Now, we still have about 30 minutes to go. What we could do is get started on the lab if you want to, if you don't want to hear me talk anymore. But I will stop at 3 o'clock and give you a chance, because that's when you got to have the test on chapter 17. Or I can get started on chapter 19, and then next time we do the trip to planetarium at Samford, if we get back here before 3 o'clock, there is time for you to take the test on chapter 18. If you don't come back, if no one comes back, then I'll just record from 19. But if you do come back, any of you come back, I'll let you take your test and the other can make it up later anytime during office hours. Okay? So what do you feel like doing now? Do you want to start the lab or do 30 minutes worth of chapter 19? Say again? I can't hear it. The lab? You do want to do the lab. Okay? Then what I'm going to do is, I wanted to do that. All right, as soon as the PowerPoint will wake up, here we are. It did wake up pretty quickly. So let's go from current slide. We'll start 19. That means, okay, let's go over this quickly, if I can do anything quickly. Tuesday, we'll go to the planetarium. 3 of you will be going, right? We'll leave here. If you're here, we'll leave. Is anyone going to leave from here? And you want to follow me there?
What time are you leaving from here?
I'm leaving here right at 12, as soon after 12 as possible. You want to ride with me? You do? Okay. So I'll wait for you up here in my office. Up here?
Yeah.
Okay, up here. I'll come up here. I'll be up here at 12, and then and the other 2 of you are driving. Is that right? Okay. Well, then we'll ride together. Then you'll come back here with me when it's over with, right? James? You'll be coming back with me then when it's over with, okay? I thought you said you live close by and you were just gonna go straight for it.
If I drive, I'm not coming back, so.
Right,
I don't
okay.
wanna miss anything, so I'll ride back.
Okay, all right. Okay, well then, when we get back, if you wanna have the test on 18, you can. If you'd rather wait and, we'll continue on 19, we'll do that. But here's chapter 19, building the Earth's surface. Okay, and let's think about what happened here. Okay. We talked about rocks and minerals that make up the Earth's surface. Then we talked about plate tectonics, which has part of the role in making the Earth's surface. In this chapter, we're looking at building the Earth's surface. And a lot of what we're doing now comes right from the last chapter. The core concept is the surface of the Earth is involved in plate tectonic processes, the last chapter, that result in an ongoing building up of the surface. Okay? They show here, I think that's Mount Shasta. No, Mount Shasta or Rainier. I don't remember which one that is. My book doesn't have it. This is an older edition. Anyway, it's one of the volcanic mountains, probably in the Pacific Northwest. And that's an example of building up the Earth's surface. It's been a long time since that one had an eruption, but previous eruptions made all this lava flow here, you can see, and on here and here, and that built up the Earth's surface. So this chapter is talking about building up the Earth's surface. The next chapter is going to be about shaping the Earth's surface, which basically is wearing down the Earth's surface, okay? So these two chapters, they come from the last chapter, plate tectonics, but they are contributing to, they go together, building and then shaping. So how do we interpret the Earth's surface? The major principle mentioned here is the principle of uniformity, okay? And the shorthand version of this, the present is the key to the past, okay? What does that mean? What is happening now basically is showing what happened before, okay? There's going to be another one we'll talk about a little bit later. I can't remember if it's this chapter or a later chapter, which is very similar to this. But anyway, rocks are changed today by the same process that changed them in the past. Igneous rocks are formed by volcanic activity or whatever. The sedimentary rock are made by sediments, both plastic and chemical, same as they did in the past. Metamorphic rock or other rock that are undergoing, by heat and temperature, changing the crystal structure and becoming different rocks. So they're being changed today by the same processes that changed them in the past. Before, they thought there were some sort of catastrophic models of what had happened in the past, that's what previous thinkers, that made the Earth's surface what it is, and then it hasn't changed. No, it's always changing. The change is just so slow sometimes we don't realize it's changing, but it is. It is always changing. The catastrophic events contribute nonetheless. We still have volcanoes, which are catastrophic. Don't tell the people in Pompeii that Mount Vesuvius wasn't catastrophic. It was. We still have earthquakes. Don't tell the people in San Francisco, oh, that was just a little thing. No, that was pretty catastrophic, but that's always been going on. And those folks who live somewhere out there in Siberia when that last asteroid or meteorite impacted the Earth, that's happened before, it will happen again. Okay, fortunately it was out in an area where no one lived close by, and it just caused a big surprise, but no one, I don't think, was injured or hurt or anything else. But catastrophic events do occur, but they've always occurred. That's not how the Earth was formed. Well, originally, yes, but it's not been a series of those. They have happened, but they've always been happening. And here is the other term, diastrophism, the process of deformation that changes the Earth's surface. It produces structures such as plateaus, mountains, and folds in the crust. So we will talk about these kind of changes that are going on. Diastrophism is also related to volcanism, which is the movement of magma, basically volcanism, and earthquakes. And by the way, those two go not always together, but they are related to each other pretty closely. The basic working theory is that of plate tectonics, which is the whole last chapter. Okay? Diastrophism is this process of deformation that changed the Earth's surfaces. Okay? Whereas principle of uniformity, same thing that's happening today, that's what happened in the past. Same thing that happened in the past, still happening today. So let's look at basically the way to look at this, I think, is cause and effect. Now, if you have the new book, before we get here, there is a picture of Mount St. Helens. That is a 1982 image of Mount St. Helens near the Seattle in Portland, I think closer to Portland. Mount St. Helens is the most notorious for its eruption May the 18th, 1980. This picture was taken 2 years later. It's still stinging a little bit, okay? It happened at 8:32 in the morning when it became the deadliest and most economically destructive volcanic event in the history of the United States. Does that mean it was the biggest volcanic event? No. It just means it was the deadliest because more people were living around it that used to live around them, okay? Most economically destructive because it destroyed bunches of timber, bunches of apple orchards, and lots of things like that. Destroyed a lot of material. But you know what? The soil that was deposited there after the eruption over the next 10, 15, 20, 25 years has now become richer soil than what it was there before because you have lots of new minerals that came up. So what was deadly before is now also part of the enrichment. Same thing happened. Now this is a completely different subject, but I can remember my wife's family used to take a trip to the beach about every 2 or 3 years, in the summertime, occasionally in the fall or other time. And usually when we went, we always went by to get us some shrimp. And one of those trips, I think, was shortly after Hurricane Ivan, or one of the earlier storms. And we went by to check it out, and they said, "No, there's not really very many shrimp this year. They got wiped out by Ivan." We said, "Wow, that was really bad, wasn't it?" And they said, "No, not really." He said, "The shrimp beds, or whatever you call it, where they were reproducing, were really getting nasty, and shrimp were dying off. It needed a hurricane to come in and clean out the system." And he said, "In a few years, we're going to have better shrimp than we ever have." And sure enough, that happened. So nature has a way. Sometimes the deadliest thing that happened is also replenishment, making for new growth in the future. Okay? Happened with Mount St. Helens as well. It was deadly when it happened, but a lot of good things have come out of it. 57 people were killed. Hey, that's not a huge number, but from a single volcano, the most we've ever had. 250 homes, that's terrible, okay? 47 bridges, that's expensive. 15 miles of railways, that's expensive. And 185 miles of highway were destroyed. That's what made it so expensive. 57 deaths, that's bad, but guess what? I mean, you get more people dying of that from shootings than any major city. I mean, I just heard Chicago had already passed a couple hundred shootings this year, so 57 is not, it's terrible that it happened to those 57 people, but compared to other things, what's that? Oh, I thought someone said that. Okay. I may be getting in trouble. Shut up. Okay, now. So this is the cause and effect type stuff. Stress, I think of as the verb. That's what's doing the action. Strain is the noun, which is the object of that action. To get English class in here, okay? So the stresses are what's happening. Those are the forces tending to compress, pull apart, or deform a rock. Okay? Does that sound familiar? compress, like converging, pull apart, like diverging, deform, like transform. Very similar. 3 stress forces, the action, the verbs here, compressive stress, when you're pushing things together, plates moving together. Before we called those converging plates, now we're calling them compressive stress. The force resulting from converging plates is a compressive stress, the force. Tensional stress are when they're being pulled apart. That's like the diverging plates. That's the stress that formed as a tensional stress, pulling apart. Okay? And then the shear stress is the stress that you get when the plates sliding past each other. That was like your transform boundaries. Okay? So these 3 match the other 3 very perfectly, but these are talking about the forces or the stresses that are feeling. That's the verb. That's the action. What are the nouns coming from that? The strain. What is the adjustment to the stretches? Again, there's 3 types. They're not related to these 3. Any one of those could be all 3 of these, or any of the 3 here. Okay? So, the first type of strain is elastic strain. Okay? Believe it or not, I'm pushing on that desk. Okay? If I'm pushing at it, I am in some very small way compressing it. But when I take the pressure off, it comes right back like it was. In fact, I don't even notice it did anything. Okay? A tennis ball. You hit a tennis ball as hard as you want to. If you took a picture of that when you hit it, you see that ball flattened out. Your tennis racket bulged. But guess what? When you finish your stroke, the ball comes back to being just like it was. Your racket comes back to being just like it was. That's elastic, meaning it returns to its original shape. So rocks do stress, whether they're compressive, tensional, or shear. They do stress, but the strain produced when it goes back to the original shape, that's an elastic strain. It goes back the way it was before. Now, I bet you when you think elastic, you think something that stretches. Well, the key is not that it stretches, it comes back to what it was before it stretched. That's what makes it elastic. The second of these is plastic strain. That's when something is molded or bent. Okay? Do you remember the old Saturn commercial where the kid is throwing his basketball against the car door? And the Saturn supposedly always came back to its original shape. That was elastic stress. But if he threw it just a little too hard, or maybe too hard of a ball, and threw it, they didn't show this in the commercial, and it actually bent the metal, that was plastic strain. Elastic strain, when it returns to its original shape, plastic strain is when it can't. It actually gets molded or bent out of shape. Does not return to the original shape. And rocks do that as well. Okay? They will bend, or we'll see examples of that. The third type of strain, result of the stresses, would be fractional strain. What happens? It actually breaks. It doesn't just bend or mold or something like that, or return, it actually breaks. The rock cracks or breaks, and therefore you have a fracture strain. 3 types of stresses, each of these could do any of those 3 types of strain. Any of the 3 types of strain could come from any of those stresses. But those are the strains. Okay, we will start next time with, because it is time, with the stresses and deformation. Okay? Trying to find where the slide is. Okay. This is top of page, the second column on page 483. We will pick up and go from there next time. Okay?